Hello, students. Today we discuss about kinematics in one dimension, which is describing motion. That is, we identify what are the physical quantities which differentiate one motion from the other motion. So, for describing the physical quantities, we need to have a reference frame. For example, if you are sitting on Earth, we are stationary with respect to Earth, but moving with reference to Sun because Earth is moving around Sun. Then when we move, we get displaced, and we need to understand the difference between the distance that we move and the actual displacement. Sometimes we may be traveling. Suppose we go to a place and come back to the place where we started, that displacement is zero, whereas we would have traveled some distance. So this distinction we need to understand. Then we need to define what is the velocity. That is the how fast we are moving, in what direction we are moving. So we need to define this quantity, which is instantaneous. That is, this quantity may be changing with time. So we need to define instantaneous velocity, average velocity, then the velocity itself. When it changes, we call it acceleration. Then we will arrive at equations which show relationship between the various physical quantities of motion. So when the motion is of constant acceleration, then we look at the cases of falling objects under the field of gravity. Then finally, we see how do we present this graphically. The motion is presented. The reference frame, here we see the reference frame. Let us take the case of a train which is in motion, and the people who are sitting in the train, they are stationary with respect to the train, and the two people who are sitting, one is stationary with respect to the other person, but both of them are moving with respect to a person. If you imagine is there on the ground, then they are moving with respect to a person on the ground because the train is moving, and you look at the other person who is moving within the train. Now that person has some speed with reference to the persons who are sitting in the train, and the speed of the person with respect to a person on the ground is different than the speed of the person with respect to the persons who are sitting in the train. So the physical quantities will be different when you choose a different reference frame. So it is necessary, therefore, that we identify a reference frame before we express the physical quantities. So this is a case where we have taken a reference frame as a line, a point. Actually, in one dimension, the reference frame is only a point. When we talk about a two-dimensional motion, then the reference frame will be two axes. Generally, we take about the Cartesian axis, or we can take polar coordinates, or we can take cylindrical coordinates. Different depending on the type of surface or the space in which the object moves. But in our discussion now, we are discussing only the motion in one dimension. So we take a particular point. So now here we have taken a point, and then in this case, we are representing the motion of an object. It moves right 70 meters and comes back 30 meters. So effectively, it is displaced by 40 meters. So here we say the displacement is 40 meters, and in this case, the displacement is towards right. Suppose if the displacement had been towards left, then we will say 40 meters to the left, or we can even say that it is minus 40 displacement, and the right side is plus 40 displacement. So displacement, when we specify, we not only specify the magnitude, that's 40, that's the magnitude, 40 meters is the magnitude, meter is the unit. We also specify the direction. When we say plus, it means one direction, minus is another direction. In case of one-dimensional motion, there are only direction, either forward or backward. But when we discuss two-dimensional motion, then there can be many directions. So that we will see later. So in this case, now we see the distance it has traveled is more than the displacement. The object is displaced only by 40 meters, but it has traveled a distance of 70 plus 30, 100 meters. The distance is 100, whereas the displacement is 40. In case the object or the person had come back to the origin, then the distance would have been 140 and the displacement would have been 0. So that distinguishes between displacement and distance. Distance we say is a scalar quantity because we only see the magnitude. There's no direction. We don't say plus or minus. Whereas the displacement is having both magnitude and direction. And in case the motion is only in one direction, if there is no change in direction, then the magnitude of displacement will be the distance. Now, for example, had it moved only, let us say the object stopped here, then we will say the displacement is plus 70, but the distance is 70. Suppose if the object has moved to the left, then we will say the displacement is minus 70 and the distance is 70 meters. So that is how we define the displacement and the distance. Here we have the case that we talked about, the positive and negative displacement. The displacement we define as the difference between the final position and the initial position. X2, X1 are positions. So always the subscript here, the bigger subscript refers to later times. So X2 is later time and X1 is earlier time. So if the object is, for example, it started here, this is that means here we are starting, this 0 refers to only the 0, this y actually has no meaning. We are talking about one-dimensional motion here. Now, so this is what is shown here is distance, and here it starts with time 0, then moves in this direction. So x2 minus x1. And here it starts here and moves in this direction. So this displacement is positive, this displacement is negative. Suppose now we will come back to this after we see look at the definition of velocity. So the speed and velocity are the quantities which are defined with respect to a particular motion. The speed is nothing but the distance by time, whereas the velocity is the displacement by time. So if we go back to the cases here, now in this case, let us take this journey takes about 2 seconds. So in this case, the displacement is positive. So the velocity will be plus, suppose it takes 2 seconds, then 20 meters, the velocity is plus 10 meters per second, whereas in this case, the velocity is minus 10 meters per second. So the velocity we are showing with a sign, that is we are showing the direction and the magnitude, whereas distance is only magnitude. That means the speed here is 10 meters per second and speed here is also 10 meters per second. So in these both cases, the motion does not involve a change in direction. So in such a case, the magnitude of the displacement will be same as the distance and magnitude of the velocity will be same as speed. For example, here it's plus 10 and 10 is the speed, here velocity is minus 10 and the speed is 10. So, but we look at the further previous case. In this case is interesting because we see, suppose the entire time it has taken about 4 seconds, then it has traveled a distance of 100 meters in 4 seconds. Then we say the speed is 25. 100 is the distance by time, 4 is 25 meters per second is the speed. Whereas the displacement is only 40, which is positive plus 40. So we say velocity is 40 by 4 plus, that is plus 10 meters per second is the velocity, whereas the speed is 25 meters per second. So this, I think, makes you clear the difference between displacement, distance, velocity, and speed. And the quantities like speed and distance are scalars, and the displacement and the velocity are vectors. Now we define, what we have defined was the velocity, which we call average velocity. That means over a time period. but the velocity may be changing every instant. Like when you are in a car, what you look at is the speedometer is the instantaneous speed, and if this car is moving on a single track in a single direction, that will be the velocity. The magnitude of the velocity is what is shown in the speedometer, and we will say, because the direction is not changing, if it is moving in the positive direction, we will say plus but the magnitude of the velocity will be same as the speed. Now here you look at the two diagrams. In the first one is a constant velocity case. This average velocity, this is constant. And in the second case here, we see the velocity is varying with time. Initially the velocity is increasing, then it is constant, then it is decreasing, then it is constant, then it falls to zero. So here, this is average velocity. How do we get average velocity? Now, the distance, that's the displacement that is traveled by the displacement that is traveled by the object is given by the velocity around that point. So this is velocity which is constant, and here it is, this is constant, here the velocity is increasing, here decreasing, this is constant, then it falls to zero. So the displacement actually we get, because this is a definition of the velocity, the displacement, this is a displacement, beta x, this is nothing but the velocity into the time. So if we take the velocity at this instant and take this small interval of time, we multiply the time by this velocity, we get the displacement. So like that, if you do the entire time frame, then we get the area under the curve is what gives you the displacement in this time. And the average velocity is nothing but the total displacement, that is the area under the curve, divided with this total time gives average velocity. So that is the total displacement by total time is average velocity. But whereas the instantaneous velocity is the distance around that particular interval, displacement at that point of time by that small time. That is how you define as instantaneous velocity. Hope that you will get it more clear as we go along. Now we look at the cases of acceleration. Now acceleration is actually change in velocity. When there is a change in velocity, then not change in speed is not. When there is a change in speed, also there is an acceleration, but there can be acceleration without change in speed. So that we will see when we see two-dimensional motion. In case of a uniform circular motion, then that we will realize that there could be a case where there is no change in speed, but still it is undergoing acceleration, because the velocity involves both magnitude and the direction. So if the direction changes without change in magnitude, then that is a case where there is no change in speed, but still there is acceleration. Okay, so here we are considering acceleration in case of one dimension. So there is a change in velocity. The example gives us the acceleration, which is acceleration. Generally, we take it to be increasing the velocity. So here we had some velocity, and here you look at the acceleration, which is given as 15 km/h per second. That means in every second there is an increase of 15 km/h. So in 5 seconds the increase will be 75 km/h. So whatever was 0, it becomes 75 km/h in 5 seconds, because in 1 second the increase is 15 km/h. Now this is a case where this is a case of deceleration. That means the object is moving to the right, whereas the acceleration is negative. That means it is decreasing. That means whatever was 15 meters per second, it reduces to 5 meters per second in 2 seconds, because the velocity and acceleration are in the opposite direction. And this we say the acceleration is negative. And so this is a case where we say there is a deceleration. That means the object is getting decelerated. Okay. Now there is a difference. There is a difference. Yeah. So here in this case we have always when we say, as I said, the time 0 is here, and this is increasing because this is V1 and this is V2. So the subscript shows whatever is the earlier time and later time. So here it is moving to the left with the velocity 15, moving to the left. That means it has a speed of 15. Then we have an acceleration. That means the change in velocity in the positive direction. So that means it is opposite to the velocity. So it is decreasing. So that means after 2 seconds, it is becoming 5 meters per second and still in the minus. Now, after some time, you will realize that the velocity will change because after some time, now it is that is every second. For example, if you take every second, it is 5 meters per second. That means in another second, it will become 0. Then further, it will change, it will reverse the direction. The car will start moving in the positive direction. Okay, so this is a case of deceleration here because the velocity is decreasing, is deceleration. Okay, and acceleration, positive or negative, depending on in which direction. This is a positive acceleration, and the earlier thing what we looked was a negative acceleration. That's what this text tells us. Okay, so the acceleration now is now so far we have seen acceleration over a period of time that is it was not changing over a few seconds, but it may so happen that acceleration also changes, like we have seen the case of velocity, like we have seen average acceleration, average velocity, and average instantaneous velocity. So this could be the same even for acceleration. It could be that the acceleration is constant, or it could be varying every instant. So that instantaneous acceleration is defined like the change in velocity by time. When you take the time interval very, very small, around that particular time, you get the instantaneous acceleration. So, but we generally look at cases where acceleration is constant. So now the average velocity is defined as the total displacement by time. That's what I said, that's the area under the curve by time. So average velocity is total displacement by time. So the average velocity, as I said, area under the curve by the area under the curve is the total distance, and that by time gives us average velocity. So this is what it is. This is a total displacement, not distance, and displacement. We are not showing actually the vector representation that we will see in the following lesson. How to differentiate the symbol for vector and the scalar quantities. But here this we take it as a displacement. This is a total displacement. This is a time t is equal to 0, and this is a time t. This is the total time. So suppose if the starting time is 0, then we have average velocities x minus x0 by t, and this is the average acceleration. That means we are considering constant acceleration, which is v minus v0 by t. So we can take any two velocities and divide by the time between those two, then we will get constant acceleration. So this is average velocity, and this is the acceleration. Okay. So now the average velocity can also be defined as this also is defined as average velocity v0 plus v by 2, because if we have because the acceleration, this is valid only if the acceleration is constant, not otherwise. So that means where we are having an increase like this, that means a straight line, the velocity is increasing a straight line. When the acceleration is constant, then we will have the velocity is increasing, then we will see the average velocity can be defined as v plus v0 by 2. So if we use this equation for average velocity, and also use this equation and this equation for acceleration, then we can do some manipulation and get the equation for the displacement. X is equal to x0 plus v0 t plus of at square. So those equations can be combined, and manipulated to get this derivation. Just I have some problem to write with my pen to derive. So let me see if I can make it more clear in the following this thing. Okay. So that is the equation for this thing. So here I'm just showing you the various types of motion. The top diagram show you the position versus time of different types of motion. So here this is a case where position is not changing. That means this is a stationary object. You represent graphically like this. And this is where the position is changing. This is a case of constant velocity where it is moving away. Then we see the position is coming back. So this is the velocity is becoming reversed, opposite velocity. So that is the object has gone like this and then coming back like this, but with a different velocity. And here we see in the bottom diagram, this is the velocity, and this is the velocity after this time, but this is the speed. You can look at this is the velocity down and the speed is up because it is only the magnitude. And there is no acceleration. So this is a case of constant velocity. Okay, this is the position. Okay, this slope is for position, not for velocity. So this is a constant velocity. So there is no acceleration. But look at this diagram here. We are having the position is changing like this. So the velocity is actually decreasing. The reason why it is decreasing is because you can see the position change is taking more time as you move around. Okay, so the velocity is decreasing. Then it becomes zero, like we have seen one of the examples. The velocity after some time becomes zero, and then the velocity, because it is decreasing, it is changing its direction. So this is how it comes. Okay, so this is a gradual change in direction, but here this is a sudden change. It is like a ball bouncing, you know. But here it is decreasing, becoming zero. Then it is coming back. So this is a case of acceleration. So the acceleration is suppose is negative, because this we take as a positive, position is increasing, positive. So because the velocity is decreasing, this is in the case of negative acceleration. Okay, so this is just to give an idea of how do we graphically represent the motion. So the previous slides, whatever we have discussed. So finally, these equations, this equation can be derived by manipulating the velocity equations. V is equal to V0. V average is V0 plus V by 2. And A is V minus V0 by T. So using that in manipulating, we can get these basic kinematics. These are called kinematics equations, which show the relationship between various physical quantities in case of constant acceleration. Okay, so this maybe we will look at the detailed derivation later. Okay. But these are the equations which you need to know to be able to solve the problems in kinematics of one-dimensional motion. So here we are looking at the case of falling objects, and we know when we drop an object from a height, it increases its speed. Suppose, but for gravity, if you just release an object, it would have stayed there. But because of gravity, it falls down, and the falling is if there is no air resistance, whether the balls or a paper will fall at the same time irrespective of the weight. They will reach the ground at the same time. But if there is some air resistance, then there may be some lag between the motion in case of falling objects. So here, this is a famous experiment on Tower of Pisa by Galileo, where he studied the time of fall of objects, whether lighter objects will take more time or less time. These studies he conducted by dropping materials from the tower. I think that is how this the figure of tower is shown here. Now here we see as the object falls, it keeps gaining speed, and for example, in the first second it has traveled this much. Second it goes this much, it goes this much in the next second. That means that every second the distance it travels is increasing, and that is reflected in this graph. So this is a graph which is the position in case of accelerated motion of accelerated object. So yeah, here we are representing the position and the time. This is case of a constant velocity case. It will be the position will be a straight line. That means that's what we have seen in one of the cases before. The position diagram I have shown you. Yeah. So this is a position diagram. So this is the case of constant velocity. The position will be like a straight line. Yeah. So now we can see the slope of the straight line gives us a velocity. That is the important thing that you need to know is whenever there is a position, if you plot position versus time, the slope of the graph gives us the velocity at that point. For example, let us go back to this. Go back to this. Yeah, see this slope here, this is a case of changing velocity. Here the velocity is constant, but this is a case of changing velocity. Now if you take the slope, this is gives us velocity. You can see the slope is decreasing. The slope here is more than the slope here. The slope is decreasing. That's what's happening. The slope is decreasing. That means velocity is decreasing. Okay, it is decreasing. The slope is this. Any point you take the slope, it is decreasing. Here the slope is 0. Here the slope becomes negative. So the slope of the position versus time graph gives us the velocity, instantaneous velocity at that point of time is what is the point which is to be emphasized at this point. Okay, so this tells us the slope at a point is what is instantaneous velocity. So here finally there is an example. Whatever we have seen is summarized here. Now this is a case where the velocity, the velocity is constant. Then if velocity is constant, no, it's not constant. The velocity is increasing. Okay, there's a say velocity is increasing. That is a case which happened in case of falling objects. The velocity was increasing. So we had the shape of a curve. So this is the curve. This is a case of when there's an acceleration, velocity and acceleration are in the same direction, the velocity is increasing. So the position will vary like this. Okay. So that's what. When the velocity is increasing, this will be a curve. Okay. And if the velocity is constant, the position will be a straight line. Again, when the velocity is decreasing, now you find the curve is reversed. See, this is concave outward, this is concave downwards. Okay, it takes more time to travel a particular distance. That's why the curve is down. Okay, you can see this curve is shaped like this, and this curve is here. This curve is shaped like this. Though is very, very, very less, we are not able to see. But if the slope is more, then we can. If the change is more, then we can see more concavity here and more concavity here. But one thing is clear: this is concave up and this is concave down. That is because of the change in velocity. And when it is constant velocity, then the position will be like a straight line. So that's how we can analyze from the position time graph, velocity time graph. We can analyze the nature of motion of the objects. Okay, and finally, the one-dimensional studies is important because the multi-dimensional, there's a two-dimensional or a three-dimensional motion can be investigated as the three independent one-dimensional motions are two independent one-dimensional motions. So understanding of one-dimensional motion is enough for us to, to study motion in higher dimension. So this is the basic equations remain the same. Okay, and this is just to illustrate that that if you have to compute the displacement, I have said that the velocity time graph curve area gives us the displacement. So if you take these small intervals, if you decrease the time interval here, then you get the instantaneous velocity, and here you can see the calculation of displacement will be more accurate. See here, you can see the area under the curve here. If you see, if you estimate using these discrete things, different things, there will be some errors. Okay, so it is less by this, but more by this, less by this. So this is missing, but this is added. Okay, so this is missing, this is added. So whereas if you reduce this time interval, you can see that you are approximating the area better when you reduce the time interval. This is a very important point that you need to know when you actually go in higher classes for a numerical evaluation of the physical quantities, of any physical quantities, not only in kinematics, even other areas. Okay, so yeah, I think that's it. So there are some problems which we can work out later.